and we can grow cracks, they will grow by creating those wing cracks parallel to sigma 1. And that's how you're going to define this new value of D. I forgot to mention, but here alpha is just the cosine of phi, and phi is the orientation of those pre-existing crack flows defect with respect to sigma 1. So now we have a description of what is a damaged state, but of course we need some physical criterion to say when we're going to have opening or extension of those cracks. And as I mentioned before, since we are interested in the seismic cycle, we want to have a physical criterion which is consistent for a wide range of loading. So in fracture mechanics, to determine when you have crack growth, you have to compare the local stress condition at the tip of the cracks and the ability of your rocks to resist fracture. And it's basically comparing the stress intensity factor to the fracture toughness. And most of the damage model use a quasi-static or stress corrosion like crack growth law, for example, this Charles growth law. But laboratory experiments that have been performed on rocks and a high loading rate have shown that we actually have a fracture toughness which is sensitive to loading rate and crack tip velocity. So here you see we have two different figures. We have one for the dynamic initiation toughness, so that's the resistance to fracturation, and the dynamic propagation toughness. So if I'm focusing on this one, little is known about the initiation mechanism of a crack, but based on microstructural observation, what people believe is that we have we have dislocation processes at the defect level, at the level of the structure of your mineral, that will accumulate until they are connecting and they are creating this new surface. And what has been proved is that depends, of course, on the local state of stress, but also how it reaches this critical value. And therefore, this dynamic initiation toughness, when you are creating this new surface, depends on stress, but also on the loading history. So that's the loading rate dependency of fracture toughness. And once the crack is initiated, it has been shown that what we call the propagation toughness. So here you already have the surface that is creating, and you are propagating the cracks, and that depends on the crack speed. And that requires a monotonic increase of the propagation toughness. So in short, if you're increasing your loading rate, it's becoming more and more difficult to initiate and propagate cracks. So when you're trying to model damage during earthquake, you need to include this dependency on crack tip velocity and on loading rate. And that's really the essential difference between the model I'm presenting today and the one that were previously published. So effectively, that's what we do. So in each part of the model, like in each cell, we're going to have a local state of stress, which depend on the background loading, but also on the rupture propagating along the fault. And for each cell, we're going to compute a stress intensity factor at the tip of the crack. And we'll compare this stress intensity factor with some laboratory value of fracture toughness. And if you have the two which are equal, then you can have a propagation of your cracks. And we are solving the following equation. We want the stress intensity factor to be equal to the propagation toughness. And when those two curves are meeting, That's the equation we are solving. We are getting the crack speed because the dynamic propagation toughness depends on the crack speed. And what is the crack speed is just dl, which is the length of your new crack, over dt. So that's effectively how I'm defining the new length of my cracks by solving this equation. So I'm getting a new d. Please, if you have any question, interrupt me. Maybe it's a lot of information. So now we have...
Marion, I do have a question. So your computation of the dynamic stress intensity factor, it is a dynamic calculation?
Yes.
Yeah, okay. But using this equation, you do not, is it true that you don't have to resolve wave propagation on the scale of these cracks?
No. Effectively, so that's... I didn't detail for this talk how we are computing the stress intensity factor, but this is a quasi-static solution. So we are computing, we are looking at the stress on this initial cracks, and if we can slide, we are going to compute the change of stress at the tip of the cracks due to this sliding. But we are not taking into account the wave propagation. It's a static computation. And another thing that we are evaluating is, and it's not on this graph, is the connection between those cracks, because as the cracks are growing, you have interaction between cracks, right? And that also is going to change the stress intensity factor. So that's the two parameters we are computing. And then this is a static value of stress intensity factor, and we multiply it by this ratio, which depend on the crack tip velocity.
Okay, thanks.
That's what I call the dynamic stress intensity factor. I hope it answers your question.
Yeah, thank you.
Okay. Marion, may I interrupt you for a while? And
Sure.
just
I can't see who is talking.
Wojciech Debski, I'm sorry. Okay, I was. Oops. Okay. Can you see me? No, something. Oh, right now it should be. Marion, just simple question. Is it calculation 2D or 3D? Do you consider crack in 3D or in 2D?
No. It's 2D.
Okay,
so it's in something in between, because the value of D is kind of 3D. But
no, but you have no free degree of freedom, only 2.
No.
That's what. Okay, thanks.
And now that we have this new value of D, which again tell you about the volume occupied by those cracks in the medium, we want to translate it in terms of the dynamic change in elastic model, which is really the goal here. And that's where we are using this energy-based approach that was developed by Rice and Hill in the 70s. So mathematically, this is equivalent to express the Gibbs free energy density of a damaged solid, as the sum of the free energy of a solid without flow, without cracks, deforming purely elastically. That's what I was describing here. And the free energy corresponding to the contribution of the microcracks. And this free energy per crack depend, of course, on the fracture energy release rate, which is the crack growth, and the surface energy to create a surface. And this its energy release rate depend on the stress intensity factor. Okay, and here we simply have the pressure ratio and the Young modulus. For our model, we are ignoring the mod 2 and mod 3 because we are considering wing cracks, so it's become very quickly purely tensile. So here it's how we are computing the contribution of inelasticity for our Gibbs free energy. And then using the law of thermodynamics, we can derive first the strain. By deriving once the Gibbs free energy, we are getting the strain. And by deriving twice the Gibbs free energy, we can get the compliance tensor. And that's really how we are computing the stress constitutive law at each time stamp for each cell of our model. So based on what I've described before, we have three regimes. Under compression, we can have, well, nothing can happen. Basically, if we are not overcoming the resistance to sliding on those initial flow, we have a purely elastic medium, no cracks are growing, so we are back to the Hooke's law, okay? And if we overcoming this resistance, we have growth of wing cracks. And this is, I'm not going to explain this equation, but is really using this, we are relating a strain to stress. And the third regime is locally, we can be under tensor regime and following the same law, we are computing a strain-stress relationship. Okay, so that's all for the micromechanical model. Do you have any questions, or can I move on, move to the result? Mm-hmm. Okay. Well, we can go back if you have questions afterwards. So here is the model setup. I'm going to start simple and build on the complexity, so we can try to analyze this feedback, this intertwined dynamic between the bulk and the fault. So I'm starting, so it's 2D modeling. It's the strike slip fault. This is the apply background stress with some angle with sigma 1 and the fault. And I have, I'm applying a friction law here. Since I'm modeling earthquake, I choose to apply a slip weakening law. And so here I have the tensional quadrant here and here, and the compressive quadrant because I have a right lateral strike slip fault. And of course, in the medium, I'm having this damage rheology that I just described. And you will see for the rest of the talk, I will always divide the dimension by the post-zone, the quasi-static post-zone size, which is the equation given here. But for the parameter I've chosen, it's roughly equal to 1 kilometer. So the first thing I wanted to explore is the impact of the rupture itself on the bulk. So again, I'm starting very simple. The material is equivalent to a granite, and I'm starting with a small initial density of flow. And I'm running a rupture. And as you can see, damage essentially occurs in the tensional quadrant of the fault. I should have had an S, sorry. But how does damage occur? Is it under tensile regime or compressive regime? So one way to look at that is by computing the invariant of the stress tensor. So here at the top, I'm plotting the first invariant of the stress tensor. So it kind of gives you the volumetric deformation. This is normalized with the stress field at the beginning of my simulation. So basically, if it goes above 1, that means I'm overcoming the compressive regime. I'm under a tensile regime. So you can see this is not happening. Here is the second invariant of the deviatoric stress tensor. And what's interesting here is I'm plotting the Drucker-Prager failure criterion, which is like the more Coulomb criterion, but using the invariant of the stress tensor. And so 0.6 is like the classical friction value. So when I'm positive, I'm expecting to have inelastic deformation, basically. And here I'm plotting what's happening in the medium at the time of the snapshot. And I have three colors that depend on the regime which is undergone by those different cells in the model. So in black, it basically stays elastic. There is no inelastic deformation. In blue, it's when you have growth of wing crack, and in yellow, if it's you have locally tensile regime. So you can see that the deformation is always happening that way under regime 2. And if you compare with the Drucker-Prager, it's a good first approximation to see where the crack can grow. So what you see is that the deformation is happening behind the rupture front. You have a bit of damage happening also due to wave propagation. And if you're looking at the cumulative picture at the end of the simulation, you see that we can compute the change in elastic property or the change in wave speed in the medium, and we have up to 30% change in S wave speed and about 28% for the P wave speed. Now, if we increase the complexity a bit, we have a different initial damage. We have similar result if instead of changing the initial damage on the two sides of the fold, if we are changing the elastic property. Let's say we have a granite on one side and some sedimentary rocks on the other side. What we see is that we have more damage, and it's expected, right, in a softer material. But what we've done is we try to compare with field observations. So here what I'm doing is that I'm running different profiles across the fault in the two tensional quadrants, and I'm plotting the logarithmic of the D value away from the fault. For the softer material, this is the background value of damage in gray. And you see that for the softer material, we are following exponential decay. And for the other material, it's following more of a power law. And this is consistent with field observation. So here it's some value of damage density away from the fold measured on two different folds in Chile by Tom Milchan and Dan Faulkner. And there is, I haven't plotted, but this power law has been described by Savage and co-author for the power law decrease of damage density away from the fault. So the next obvious step was to start with some initial damage density. So you can see that in the middle of the fault. This is obviously the final snapshot, but I'm starting with here an exponential decay of damage before running the earthquakes. And if you, so the material around the fault is obviously softer in that case. And you can see that we start having also damage in the compressive quadrant. And if we are running the same type of profile, we keep an exponential decay of damage. And we also build a bit of damage in the compressive quadrant. Another interesting feature is that we wanted to know if we could use damage in the field, basically, to have some information about the rupture propagation itself. And here we set up the friction parameter so that we can, and the inertial stress on the fault, so that we can get a super shear rupture. And what you see here is that we have some specific damage, how can I say, feature that happen. And that's actually related to the transition between subshear and supershear velocity. So I'm going to try to explain a bit in detail what's going on. And I'm going to just focus on this part of the flow because it's obviously the mirror of this one. And I'm going to try to understand what creates this feature. So here, what I'm going to plot in the background is this Drucker-Prager criterion because it's a good first order value to know where the damage can happen, right? I'm going to add on top of this graph the rupture, the velocity on the fault. And you can see this is the rupture tip. This is related to wave propagation. I'm adding some gray background that gives you the cumulative co-seismic awful damage, the damage that happened so far. And just to emphasize what's going on at this particular time step, I'm plotting in red the co-seismic damage that corresponds to this snapshot in particular. So here we are under a subshear condition, and as I described before, the damage is really happening behind the rupture tip. You just have a bit of damage that occurred due to seismic wave propagation. And here it's a snapshot that corresponds to when we have the transition to supershear. So it's even like the daughter crack is actually already quite well developed. But what you can see is that when you have this transition, almost no damage is occurring in the medium, and that is because with the damage rule we have in this micromechanical model, we take into account the loading rate dependency on damage. And as I said before, the faster you go, the harder it is to create cracks. And here we are transitioning to supershear rupture, right? So you have a competition between the stresses given to the medium by the rupture propagation, but also at which loading rate this is happening. And then, when we have supershear, the pulse here is stronger. So the change in stress is more important. So even if it's this is going faster, the loading height is faster, this you have enough stress to actually trigger damage. And that's how you're getting this particular shape of damage in the medium, where you can map the transition to supershear. So you have damage under subshear condition, you have a gap, and then you have again some damage. And of course, this is something we checked. This has been observed in the field as well. And that's one example. It's a paper that we published recently with Jorge Raja as the first author, where we have this the transition for this Kunlun supershear earthquake based on seismology were there. This is some geodetic, they use optical imagery to do some correlation and map the awful deformation. And there is one specific area where the awful deformation is much smaller, the width of the damage zone, and that roughly corresponds to the location of the supershear transition based on seismology.
Marion, can I interrupt you for a while once again? Can we come back to the previous slide?
Sure.
Okay, here you plot the damage of fault damage, which seems to be occurs after the subshear and supershear fronts. However, looking at that, it seems that energy consumed in the damaged area just after supershear front is much less than behind the normal subshear front. Is it right? Am I right?
I think so. You're talking about the red area Oh, sorry. I'm guessing you're talking about the Drucker-Prager criterion I'm plotting? Or the damage itself? I think we lost
I wonder if you understand, you're muted, Wakita. There you go.
Well, I don't know if that answers your question, but so the Drucker-Prager criteria I'm plotting in the background is really to give an idea of the state of stress in the medium related to the propagation of the rupture, right? But it doesn't tell you exactly where the damage is happening based on our law, and that is given by the red language.
Okay, I understand. Thanks.
And so we decided to plot this Drucker-Prager because this is something that is often used as a proxy for damage, you know, in model that wants to incorporate inelastic deformation, but with a less complex rheology, right? That's a first proxy. So that's why we decided to plot it that. But
no, that's fine. That's fine. That's you explain me. So thanks.
Okay. So that's also why we have some differences, because this is not the rheology we are using, right? And in fact, if you were just looking at the Drucker-Prager, with this model as well, you should expect some damage gap, right, related to this transition to supershear. This is also predicted by the Drucker-Prager criteria. All right. Should I move on, or you want to? We can go back to that afterwards if you want. I think I'm running a bit out of time. I'm planning to say too much about it. I wanted, I'm going to try to be quick there, but I wanted to really talk about those feedbacks, because that's the specificity of this model. And I wanted to show that damage, if you include some dynamic change of elastic modeling, you're going to have some feedback on the seismic rupture itself. And when it comes to seismic hazard assessment, it is quite important. So here I look back at this simple case where I just have change of initial damage density on the both sides of the fault. This is the final damage state. And here I'm looking at the accumulation of slip due to the rupture. We have the curve are plotting every 0.7 second. And here this is the slip rate on the fault. And I'm comparing it with a purely elastic model with no damage. That's the dashed line you can see. And you can see that when you account for damage, well, the slip rate is smaller in terms of value, but you also have all those wiggles that actually are related to two things. They are related to when you're creating damage dynamically, that's by itself sending waves in the medium. But also you are dynamically creating a low velocity zone, and the wave that are propagating in the bulk will bounce back and interact with the rupture itself. And that's creating a high frequency content. And if you this time start with a pre-existing fault zone, which is the case most of the time when we have an earthquake rupture, this has also a big impact, because if you compare with a purely elastic model, here if I'm focusing on the slip rate, you can see that the rupture is propagating at a slower speed compared to a purely elastic model. And that's simply because I have a change of seismic, of elastic property in the medium. So my seismic wave speed is smaller. So actually, the velocity at which my rupture is propagating is also smaller. If you look at the cumulative slip, that doesn't change much actually. The final, that's some, I don't have time to discuss, but it's important when we are considering inversion of deformation field at the surface. But in terms of accumulation of slip, that doesn't change much the story. All right, and I was talking about these wiggles and the high frequency content. And if we are plotting a synthetic seismogram, so that's what I'm going to do here. I have like 3 stations, one which is right on the fault, one in the damage zone, and one a bit away from the fault. And I'm comparing, here it's the slip velocity. I'm comparing a purely elastic case in red and with simulation with damage. And if I'm analyzing this seismogram, this is a Fourier spectra of those seismograms, you can see that I have a high frequency content purely related to damage, even at some station a bit far away from the fault. This is just a ratio to emphasize the point between the red curve and the black curve. And this is something we observe in nature, so, and in the lab. This is some field observation, a station, a near-field station for the Landers earthquake, and you see that we have a high frequency content between 10 and 100 hertz, like in our simulation. This is some lab experiment performed by François Passaleg, where they changed the confining pressure, and at the increase the confining pressure, you increase damage. And they observe a high frequency content as you increase damage. There was a very interesting, I'm trying to be quick here, but study by Dunham and co-author in 2011 that tried to explain this high frequency content we observe in nature by saying that if we faults are not flat, right, they are rough. And when you have roughness, you have acceleration and deceleration because of those local change of stresses along the fault. And that by itself should lead to a high frequency content. So the next obvious step was to have a rough fault and a damage rheology. Here again, I'm going quickly, but I explore different cases by increasing the roughness. I use the same value of front roughness that the nomenclature I've used. And I'm going to compare three types of simulation: a flat fault with pure elasticity, a rough fault with elasticity, and a rough fault and damage. And here I'm plotting the velocity field for a station which is roughly at 3 kilometers away from the fault. And here I'm increasing the roughness. And if we are analyzing the frequency content, you can see here, if I'm focusing on this graph in particular, we have high frequency content between 10 and 100 hertz on a rough fault only if we are adding damage. I'm going to pass this slide. This is just a ratio between, in dark red, this is a ratio between the black curve and the red curve. And this is very important because this is the type of frequency that can destroy like two-star building. This is an example of a two-star building for the Aquila earthquake. So when it comes to hazard assessment, accounting for damage should be included. And last bit, well, I'm going to go very quickly, but a comment I often get is that this is a very superficial phenomenon, right? Damage. And this is there is some field observation that say we have damage. Damage zone looks like a flower structure, and the damage zone is becoming narrower with steps. So that's a justification to say what should we care? What should we include that? And there was this study by Okubo and co-author with a different type of simulation. So it's elasticity, but you can have crack growth. You don't have change of elastic properties. So it's a bit of a different strategy. But what they've shown is that if the widths decrease with depth, the density of cracks increase. So we wanted to look at the effect when we account for the change in elastic properties. So we basically take our model and run it at different depths between 2 and 10 kilometers. Here, so be careful. I'm showing results, but they are divided by the process zone, and the process zone is decreasing with steps. So if I'm looking at the width of the damage zone, this is what I'm showing here. We have different simulation. There's 2 cases that we are we are keeping the fracture energy constant, or the dissipation, the friction load constant. It doesn't really matter. We are getting as well this flower structure. So indeed, like this is the Okubo et al. Study, and we have a decrease in damage with depth, and what it's something we are currently computing. Now we are computing the energy dissipated, because what they've shown is that even if you are decreasing the width, in terms of energy dissipation, this is constant because you're increasing the damage density. And we seem to have the same phenomena, because if I'm looking, I'm zooming on the damage zone near the surface or at depth, you see that the density of damage increase. So we are currently computing the energy balance. And sorry, I could not show it for today. And so as a summary, I wanted to talk again about the model, the framework that Elon Rice has developed in the 70s. This is really the framework to model the inelastic behavior and compute the effect of the deformation at micro scale that affect the macroscopic scale, sorry. So it could be used for cracks, as I've shown, but if you want to add twinning or mineral changes or healing of cracks, etc., we can use the same framework. And this crack model in particular is based on laboratory experiment, and it can be used for earthquake or slow deformation, because we have this sliding rate dependency. And in terms of results, the generation of damage we are producing is consistent with field observation. It leads to a change of elastic property, again, consistent with field observation. We, on principle, could look at a field observation of earthquake and maybe say something about the rupture velocity. So to revisit past earthquake, it's a very interesting thing. Damage, of course, create high frequency ground motion. And we explored the combined effect of complex fault geometry and damage. And damage impact the rupture over the whole seismogenic zone. And I think I'm going to stop here, because I wanted to talk about energy buildup, but that's the next step. It's to incorporate this change of bulk also now over the whole seismic cycle, because between earthquake you have healing, and if you have healing, you have you're changing also your elastic property, so you're going to change the loading, and yeah, that will affect the whole seismic cycle.
So that would be your next talk, or that will happen in the next few minutes?
That was yeah. This is really what I'm trying to develop at the moment. It's a simple 1D model here. It's based. So here, when you're using spring slider, you only have friction on the fault, right? One value of friction, one at A minus B, and the stiffness of the spring corresponds to elasticity, right? So if you're running a simple model like that, you will always get the same type of event, because you have no long strike variation of friction. And what I was this is just to build up the intuition. If you start incorporating the temporal change of elastic properties in the bulk, so here I'm showing this is some field observation of change of shear wave speed in the medium over time. So it's a transform fault in the Atlantic. And this is the value before an earthquake. You have an earthquake, you have a change, a drop in seismic wave speed. And then in the months following the earthquake, you have partial healing of those cracks, and you are changing the bulk property. And by just changing this stiffness and having this kind of healing and keeping the friction parameter constant, you can see that some slip complexity naturally emerge by varying the stiffness of your model. So that's really what I want to do is use this energy-based approach to model crack healing and look at the seismic cycle. But next talk maybe in 5 years from now.
Okay, 5 years, but you say it's the manuscript isn't prepped.
No. Just a spring slider.
Marion, thank you very much. That was really a wonderful talk. I'll invite people to unmute or turn your camera on, join me in thanking Marion before we break into questions. Thank you. Really fabulous talk.